like to give you a little bit of a flavour of what you're going to expect this evening from the lecture on molten salts. It's nice to see it's generated such a real interest. But the nature of today's talk, we're not going to actually be answering any questions per se. We're not really actually going to be stating a defined position in terms of nuclear future technologies. We're going to be actually providing some information. We're going to actually be providing some opinions. We're going to be throwing out some questions. And the aim is really, as Alistair said, to try and stimulate debate and a bit of a thought leadership piece, really, just to get molten salts higher on the agenda. Obviously, as I say, there's a Q&A session at the end of this lecture. Which is, hopefully will be nice and live. I think from the people we've got in the hall here, I think we could probably actually get some interesting questions, which will no doubt tax Barry and myself. But what we'd like to do is actually get as much contribution to the floor, because there's quite a few people with probably far more knowledge than Barry and myself of molten salts in the room. So, without much ado, let's just see actually how we're going to actually run this evening. So, first off, I'll give some background, setting some context to say actually why we are talking about molten salt reactors. Before actually going on to hand over to Barry, and Barry are going to give a bit more detail on molten salt reactors, a bit of history, where they are, their benefits, some of the challenges and hence opportunities, and start looking at what the global position is on some of the molten salt reactor development that's going on. Then he's going to hand back over to me to look at a couple of the more important and significant molten salt programs before actually seeing what does that mean as an opportunity for the UK, and harking back to some of the experience that we have in the UK and some of the things that are going on in the UK which could contribute to molten salts. So that's the tenor of this evening's lecture. So a bit of background then, just launching in, I suppose a good place to start, seeing we're talking about molten salts, and for those who don't know what a molten salt reactor is, let's start there. So let's describe actually what one is. Molten salt reactors can be looked at as a type of reactor, very much like the light water reactors. There are probably 17, 18 different variants of molten salt reactors of various designs. But just for ease, we'll use this as a schematic this evening, and this is taken from the Gen 4 International Thorium roadmap as the molten salt reactor schematic that they've used. So fundamentally, unlike most of the reactors in use today, the actual where the fuel is actually used in a solid form, either in its metallic state or in its oxide state. As the name suggests, molten salt reactors use fuel in a molten context, in a molten form. The molten fuel comprises of a chemical solution which is a mixture of actinized uranium, thorium or plutonium in their halide state. So normally something like uranium tetrafluoride, and that's actually contained within a carrier salt, and that's typically something like lithium fluoride or beryllium fluoride. On this particular diagram, you can also see there's a secondary loop here, which is, in this setup, is constituted of a secondary salt loop, which might be something slightly less exotic and really consists of something like sodium potassium fluoride. So what else is different about molten salt reactor? Well, the temperatures are significantly higher than light water reactors. The temperatures they operate at are typically between the melting point at the eutectic, which is around about 450 degrees C, if you're actually talking about eutectics which contain lithium and beryllium fluoride, up to about the material compatibility temperatures associated with materials you use for reactor components. So that's up to about 800 degrees C, so significantly hotter than light water reactors. The other advantage is that as a eutectic, salts have very high boiling temperatures. So you're talking about 1400 degrees C as a boiling temperature for salts. So you don't need to actually have these systems pressurized, which is quite an advantage when you talk about the engineering solutions associated with molten salts. But of course, they do have other challenges operating at those sort of temperatures and in the presence of salts. So, probably enough about molten salt in its general form, because Barry's going to be talking about that in a lot more detail later on. What I'd like to do is just skip through very, very quickly some background and content, some of which is common to nuclear energy as we go forward, and say it's some very common issues, so I won't take too long on it, and then a couple of specific issues around molten salts. Just looking at indicative timescales, when we're looking at molten salts, we're not talking about timescales associated with the current Gen 3 plus Gen 3 reactor program that's going on at the moment. What we're talking about is actually filling the gap between the end of the current new nuclear build program and the beginning of commercially viable fusion. So we're talking about a reactor technology which is we're looking to deploy around 2050. Now, I know some people might think you can do it earlier than that, but it's just really a general date around when commercially viable Gen 4 reactors might be apparent. That might seem a long way off, but like all new technologies, the length of time it takes for R&D programs, development programs, is quite considerable. So we ought to be thinking about it now. A couple of other things, and I mean, this is known to us all, but energy consumption. We know that energy consumption within the UK and globally is actually increasing, and this just shows the World Energy Technologies Outlook 2050 estimate of energy consumption is up to 2050, looking to double, approximately double, which is quite a challenge both in the UK and globally. So bottom line is we need more generation. But that generation has to be done in a way that's actually contributing to our reduction in carbon emission targets. So this graph just shows the diversion of what the UK energy consumption is likely to grow to in about 2050 compared to what our CO2 emission targets need to reach, which obviously reflects the 8% of 1990 levels in 2050. Plus also, whatever energy source you're talking about needs to be sustainable. We know that carbon fossil fuels are finite. They don't naturally actually help in the carbon reduction arena unless you actually have it combined with carbon capture, carbon sequestration. And they're going to get more expensive as they get harder to extract and that their availability actually goes down. And the limitations on reactor fuel can also be seen. When you talk about the fuel that actually currently supplies the majority of the world's reactor, it too is a finite resource. I mean, this is just the estimate of the current abundancy of uranium in the world, taken from the World Nuclear Association website. And that current level, which is 5.3 million tons of uranium, if we operate it through thermal plutonium, uranium-plutonium cycle, we've got about 80 years of uranium left. So that sort of drives us to new reactor technology, which is either breeder or closed fuel cycle in nature. That's unless we start looking at a different sort of fuel. And that fuel could be thorium. Thorium, although it's not like uranium-plutonium, it's not fissile, it's fertile. So you need a source of neutrons to actually start the reaction, regardless of whether you actually put it in a molten salt reactor or not. And thorium metallic fuel's been used in other reactors in experimental form already around the world. But thorium has some advantages. It's actually abundant in almost every continent in the world. And if you look at its amount, if you look at total thorium content compared to uranium, you're talking about probably about 3 times as abundant as uranium around the world. If you compare fuel-grade uranium to fuel-grade thorium, then you're probably talking about 100 times more abundant than uranium. So it does actually provide advantages, especially over the longer term in terms of a sustainable fuel. But that's only one of the actual options for molten salt reactors. I think the most important thing, and some of you in the room will have picked up this from the things you're involved with, at the moment within the UK, there seems to be a real appetite to get the UK back to the top table with respect to reactor technology and reactor development. Well, this was started off by the work that was done by Sir John Beddington in 2012 with the the Reactor R&D paper that he put together. Sorry, I've just lost my place. Which has actually led to some initiatives following on from that that's been put in place by government, such as the redefinition of the National Nuclear Labs remit, with it being a wholly government-owned organisation. The actual instigation of the Nuclear Innovations and Research Advisory Board is headed by Dame Sue Eon. And the development or the production and issue of documents such as the Nuclear Vision and the Nuclear Industry Strategy is issued by the Department for Business, Innovation and Skills. And what I'd like to do is just actually pull out a few of the statements from that report, just to actually reflect the appetite. I mean, you know, that's quite impressive in terms of an ambition and aspiration. You know, we've not seen aspirational statements from the government to that extent for quite some time. So that's really a good primer. And that's why it's quite a good time to start talking about and having lectures like this evening's lecture. But if we look actually what that's trying to attain, the last time that the UK was actually at the forefront of everything nuclear back in the 50s and 80s was a different place, a very, very different place. And what I'd like to do, just to get us into the mood, to think about how we might actually get back to that top table, just to actually really indulge in some nostalgia and have a little bit of reflection. Some of you will recognise this. Let's have a look back to when the UK was indeed leading the world, when we were opening what was then the world's first commercial nuclear power station, Calder Hall in 1956.
Calder Hall was the first nuclear power station in the world. Everybody loves a lover. The public were promised electricity that would be too cheap to meter.
Anyhow, that's how I feel. Wow, I feel just like Pollyanna.
It is with pride that I now open Calder Hall, Britain's first atomic power station.
Makes you proud, doesn't it? Hey, I see Brian smiling away there. Yeah, I mean, like I said, a totally different era. I'm not sure I saw Barry in the background then, or to do you injustice there, Barry. But just wouldn't it be great to think if 2050, if we were actually opening a UK-designed, a wholly UK-designed nuclear power station, or a nuclear power station that's actually had a significant contribution from the UK, in the UK, as part of our energy future, actually providing energy in a sustainable, safe and reliable way. And I must admit, personally, from a personal perspective, if it was 2050, it'd be a fantastic 90th birthday present. That's just assuming I'm still around, of course. But getting back to what we're talking about, I've already said that the world was a different place. And if we look back to the drivers and constraints that are actually around at the time when the UK was, in fact, one of the leading nuclear reactor designers, it was actually in an atmosphere which actually had some different national and international imperatives. The requirement to actually, especially from the US, and as we all know where it sort of came from the light water reactor program, the imperative to actually have compact, flexible reactors for the submarine program was actually a real driver. And you can actually track back most of the actual today's reactor designs to this requirement for military application, and indeed the actual reactor designs that supported plutonium production for the weapons program. But if we're doing things differently, if looking at things today, would we do things differently? Would the drivers be different? Would the imperatives be different? And some of those drivers I'm just putting up here, and Barry will actually talk about them a little bit more detail later. But are there things like, we need intrinsically safe reactors. We need them to be proliferation resistant. Production of less hereditary waste. So can we get reactors that actually do not produce transuranics as part of their life cycle? security, supply and sustainability. And molten salt reactors do actually answer some of these questions. So what are the options going forward, and what will the future look like for the UK, and what could we do? Do we persevere with the current light water reactors, Gen 3 plus reactors that are currently being built with their 60 to 80-year lifetimes if you talk about life extension, with the knowledge that you could actually get improvements on those designs by actually having light water reactors with greater passive safety features and more simplicity? Or do we actually look to continue with the uranium plutonium, but we're on a closed fuel cycle rather than an open fuel cycle? Or do we look to build upon other UK legacy technologies that we have in abundance through our sodium fast reactor program, doing Ray there, and our high temperature gas reactors? We do, for instance, actually, the current fleet of reactors that are actually, the AGRs are gas reactors after all. Or do we do something different? Do we actually look to a new technology, a different technology, and a different fuel application to address that long-term requirement for sustainable nuclear energy? And again, addressing that last question, are molten salt reactors the answer? So enough scene setting from me. I'll now hand over to Barry to talk about MSRs in more detail. Thank you, Paul.
Well, first of all, thank you very much for everybody cutting out so much time to come here tonight. It really is reassuring to see such a team on molten salt reactors, and thank you to Atkins for offering me the chance to speak. And you may have spotted that Paul is offering the reasoned, the sensible and the considered approach, and you may find me controversial, although I hope not. I'm trying to be downright provocative, even offensive. And at the run-through, I noticed afterwards Atkins have engaged a professional with a tranquilizer dart in the projection box in case I go too far. So if you hear a foot noise and I slump to the floor, Paul is going to carry on as though nothing had happened. And it's just my opinions I present and nobody else's, certainly not Atkins, who I applaud very sincerely for offering this opportunity to debate and open our minds to the problems of the future. I've developed an enthusiasm for molten salt reactors, especially those fueled by thorium, because I believe that, as Paul says, due to its heritage, we have followed completely the wrong technology, and the world's nuclear industry has essentially failed. And I say that with trepidation, as I'm surrounded by high priests of nuclear in one of the great temples of our industry, and those who are working many long hours to bring in a new generation of nuclear reactors. No concrete's been poured yet. A new generation of nuclear reactors in the UK. More power to your elbow. I wish you every success. I'll start with the founders of fission. These worthies, Otto Hahn, Strassmann, Frisch and Lisa Meitner, 75 years ago discovered barium in a sample of uranium that had been bombarded by neutrons. And thereafter hangs all our industry. But the world now can currently boast about 440 nuclear power plants. But the average age is between 25 and 30 years, and they're steadily getting older. 4 reactors came into service last year, 3 in China, 1 in India, and 4 went out, all American. And there's a lot of American reactors looming towards the end of their life. If we remove the very bullish projections of principally China and India, not because I disrespect those powerful and energetic nations, but because their numbers are huge compared to everybody else, and they're also building vast numbers of power stations of all types, then certainly against the progress and build of other energy sources, planned new nuclear is essentially negligible. And I'll leave that blasphemy with you, but I'll return to it later on. To offer a comparison of what success would look like for an invention, it's only about 100 years since 2 bicycle mechanics from Ohio demonstrated a single-seat aircraft. It cruised at a maximum altitude of 2 meters and had a range of 200 yards. Last year, there were 3 billion passenger journeys worldwide. If that's not enough, consider the transistor, the computer. Sliced bread was invented in 1928. We haven't gone very far with nuclear in the years. So why isn't nuclear fission filling the lion's share of the world's energy production? It's not because it's not an eminently usable source of energy. Of course it is. But because, as Paul said, it is rooted in, the current technology is rooted in nuclear submarine propulsion plants and weapons production factories. The world did notice this and came together in the year 2000 to look beyond the current concepts and technologies. And a roadmap, we all need roadmaps, and we need pathways, and we need surveys, anyway. And this was completed in 2002 under the auspices of this group called the Generation 4 International Forum. Okay, the founder members were Argentina, Brazil, Canada, France, Japan, the Republic of Korea, the United States and the United Kingdom. Since then, the charter has been added to. Others joining have been Switzerland, Euratom, and most recently, China and the Russian Federation. The UK were founder members. We are charter members. The original date, we haven't done anything at all. We send a person over there now and again to sit at the meetings and take notes and touch, but we haven't done anything at all. The vision that the designs that we're going to choose would be in deployment phase between 2015 to 2030. 2015 is going to be a bit of a call, isn't it, really? And they looked at a huge number of designs, and these were the 4 basic parameters that the selection. They actually were subgroups of these, subsets of these, but these were the 4 basic ones. Under the heading of sustainability was availability, effective fuel utilisation, worldwide deployment, minimisation of nuclear waste and a reduced stewardship burden. Under economics, the new designs should show advantages in terms of life cycle costs, levels of financial risks, comparison to other major projects. Under safety and reliability, you would expect this to be a big one. The key aims were excellence in safety and reliability terms with low likelihood of core damage and eliminate the need for off-site emergency response. And of course, proliferation resistance, and I won't go into that in detail, but you've got that, you know what that means. The types selected, and I think they started with 200 and worked their way down to these 6 types. The very high temperature reactor, supercritical water cooled, you can read them all. I don't need to read them out, you can read them all. And the standard depiction of the first 5 are these, and this is perfectly available, and they show those designs, or really artists' impressions or conceptual drawings of the first 5 of those designs. I don't propose to discuss them here. By the way, the very high temperature reactor and the supercritical one are operating in the thermal region, so they will need a set of fast reactors to provide them with fresh fissile material. But the others are breeders anyway, or could easily be so configured as breeders. Some aren't being progressed at all, as far as I know. Others are being, in some senses. And some have very prominent and powerful advocates. The French, for example, are spending on the sodium-cooled fast reactor, 650 million euros announced in 2010 for Astrid. Presumably that's on a refusal to be beaten basis. But never mind. Notwithstanding the influential supporters of these, and some are very influential, it is my opinion that these 5 remain cul-de-sacs. Alluring cul-de-sacs, expensively promoted cul-de-sacs, but dead ends nevertheless. Why? I think we have to ask, are these once through or part of a breeder cycle? Now we could argue about the amount of uranium-235 in the world, and that's exercised many people. And there have been innumerable arguments about which reactor families would exhaust the U-235. But uranium is only about as abundant as tin. And only about 0.7% of that is 235, and that has to be extracted or separated by exotic means. Now, we could discuss seawater at length, I hope not. But if these devices are intended to be successful, and sometimes I can't understand, is the intention to have a lot of them? I presume so, in which case, to take a reasonable quantity of the world's energy need, there'd have to be hundreds, nay, thousands of them. So I think for long-term stability, the answer would have to be breeder. And the next question is, what isotope would that be then? Innocently, I say that. Sometimes I hear euphemism. People say there would need to be a closed fuel cycle. The answer is it's plutonium-239. For the vast majority of the human race, plutonium is the isotope of Satan. So it's plutonium-239. Now understand the consequences. If these things are going to be in widespread use, that is deployed by the hundreds or maybe the thousands, then there are hundreds of facilities for the conversion, the recovery, the storage, the processing, the fabrication, and thousands upon thousands of movements of plutonium. Now, as somebody who has had the doubtful privilege of trying to move a lousy SAF keg in a HSV a few hundred yards outside a nuclear site and see half the police forces in Europe get their leave cancelled, you would know that transport of plutonium is not an easy topic at all. And it's unlikely to get much easier, and needs to require thousands of them. So my view, and this is the controversial stuff, is the human race will never allow a plutonium economy to emerge, no matter what the supposed benefits. And anybody, any worldwide nuclear community that is working towards a plutonium economy is going to condemn itself to another 50 years of frustration and disappointment like the last. It's as though the chemical industry would come forward and propose that motor vehicles were going to run on cylinders of sarin nerve gas. They wouldn't get very far. It would peter out, and for exactly the same reason. Some people tell me that the world will need to be persuaded of the benefits of plutonium, and it's an advocacy problem. One of the faults of our community, our nuclear community, is we are very deterministic. We expect a yes or a no. This is the planet Earth. There is no World Nuclear Safety Committee. There is no Wizard of Oz behind the curtain. There is nobody to say, no, stop it, go and do something else. What there will be is decades of minor frustrations, little delays, questions, obstacles, maybes, perhaps a bit of unobtrusive sidelining. That's what will happen if we persist in pursuing a plutonium economy basis. Because I want to talk about another element. Now, thorium and its use in molten reactors is an interesting topic. Thorium has had a checkered press over recent years. It was seized upon by many writers on the green end of the spectrum a couple of years ago, maybe 3 or 4 years ago, as being nuclear without all the nasty nuclear bits, sort of a additive, colour and free nuclear. But these were writers whose scientific attainments were such that they think Ohm's law is a detective series. So then there was the inevitable anti-thorium backlash. The truth, as always, is much more complex than can be depicted in 140 characters or less, which is what the world seems to want these days. The reason I labour the point in discussion on molten salt reactors is the first 5 of the Generation 4 concepts employ solid fuel elements and are forced to theoretically they could, but sort of forced to use the uranium-238 to the plutonium-239 breeding cycle, rather than thorium-232 breeding to uranium-233. It's more difficult to use that for solid fuel because some of the uranium-233 created from the thorium captures its spalls, but it captures another neutron, then spits out 2, to degrade to uranium-232, which has a decay chain down to Thallium-208, which is a very strong 2.5 megaelectron volt gamma emitter. And I put it to the court, assembled here, that such a consequence is a serious impediment to the fabrication of thousands of tons of fuel elements. I know some U-232 fuel elements have been made, certainly for the molten salt reactor experiment, but they were made by skilled technicians in very small amounts, in hot cells, carefully supervised, not at the industrial scale. And I declare that although it's theoretically possible to make uranium-232 fuel, practically it is going to be extremely hard or impossible. The same science, of course, makes fabricating a weapon difficult. Now, this view has been challenged, and I've read some authors who say it could be done, and some authors who say it can't be done. I suspect the authors started with the answer they wanted and worked backwards. It would all depend on how much material you had, what its quality was, how aged it was, what style of device you were making, and how many workers you were prepared to sacrifice. One writer estimated a dosage of between 1 and 2 sieverts an hour for a weapons amount of 232 in equilibrium at a range of ½ a metre. You have to work quick to make your weapon out of that, I would say. There we are. My own opinion is we need a bit of money. There are people I would trust in this field, some health physics people whose names I know, I trust them. And I think we can probably get a reasonably definitive advice on whether a weapon out of 233 in the presence of 232 and therefore thallium was obtainable. And I won't go into technical details, but someone might ask the protactinium question. There's always somebody who asks the protactinium question. So molten salt reactors could be operated to operate a plutonium cycle. But as the fuel is molten and is usually continuously introduced in a separate reprocessing loop, then the problem of creating gamma-active fresh fuel doesn't arise. The thorium, to be frank, the thorium element, thorium, and the molten salt reactor seem almost made for each other. And if they could be successfully deployed, I put it to you that many of the drawbacks faced by the current generation of nuclear could be, with some huge effort, be made to answer what I think is a nuclear exam question, which we have seen before. And that is not to think of fission from the history we have of Admiral Rickover and his Westinghouse S2HW reactor that fitted nicely into the reactor compartment of USS Nautilus and then grew very large, but one that answers the exam question. And the exam question, I think, for the end user, the human race wants something like this. It needs to be safe, above all safe. We have two in this level 7 events. That is, 2 chunks of the Earth's surface which are not habitable anymore under normal circumstances. And there has to be no possibility of another in this level 7 event from a reactor by any conceivable or even inconceivable route. I think no movement of irradiated materials to or from the generation site. That is, fresh thorium, but nothing back, no irradiated material back. No movement of SNM. I assume you know what SNM means. Special nuclear materials. That is stuff for which you can make a weapon. To or from the site, or to any fuel fab plant. I accept that. Perhaps for a fuel load, a starting load, you would have to take an amount of SNM to the point of generation. Maximum possible barriers to the abstraction of nuclear matter, especially SNM. Minimum waste arisings, and those as benign as possible, and an end state that is acceptable, like an inert block, preferably holding all the fission products and lanthanides that were created from friction. And I've said cheap-ish, and I've said ish because we haven't seen the benefits of such a reactor yet, because we haven't got a plausible design for one yet that we can cost up. Because benefits go with cost, and I hear so many people talk about the cost of molten salt reactors. Can they compete with LWR? We can't possibly talk about competing with LWR because we haven't got a benefit cost basis to talk from. And if we cast our minds back to that Carolina beach in 1903 and asked Orville and Wilbur, well, Orville, what do you think the market will eventually be prepared to pay for this gadget you call an aeroplane if it ever becomes popular? I don't know whether they would have got between them the correct answer. And a Boeing 747 with average options will cost you $350 million, and they've sold hundreds. So let's not worry about the cost and put us off by the cost until we've seen a plausible device and what it can and can't do. The molten salt reactor says we've seen this picture before. It's one in which essentially the fuel and coolant are in liquid form. 3 main systems: a molten salt core, or the containment, some heat removal and power conversion system, which we've cut off. I mean, you could put a Brayton cycle, you could put a Rankine cycle, any sort of cycle you want on the end of that, and a salt processing and cleanup system. Now, this isn't going to be a very technical review of molten salt. This is sort of a primer because you can get deep quite quickly. It's a bit of a scene setter, and it's a bit of a call to arms, as Paul has said, to get the UK into this very, very promising field. There's a number of options. There's a number of choice of configurations and materials under these headings. Paul said there's about 17 or 18 different concepts and artist impressions out there, all stoutly defended by their inventors, who equally stoutly denounce the other 16. And I'll cover the science of it shortly. But I better mention 2 that have worked. These aren't theoretical devices, these have worked. This is the first one. They were operated under the supervision of Alvin Weinberg at the Oak Ridge National Labs in the 50s and 60s. This was part of a program towards an aircraft, a nuclear-powered aircraft, no less. My word, things were different then. In 1954, 2.5 megawatt thermal, ran for 1,000 hours, fluoride salt, as Paul said, primary coolant. It had a beryllium oxide moderator and a secondary coolant loop used liquid sodium. Superseded by a much bigger contraption, and for a scale, there's a nice chap there. I have got a laser pen, which I was only going to use to blind difficult questioners, but I will point out the man that showed the sort of the scale. 8 megawatts thermal, 65 to 68 it ran, 30% enriched U-235, ended up running a bit on 233. Its longest power run was 6 months. That's not bad. I have to say, I went to the Culham, the site of our fusion, toroidal fusion device. Their longest power run is 10 seconds, and they're thrilled to bits with that, I have to say. But there's still a long way from a workhorse power plant for the world. Some advantages. Negative thermal and salt void reactor coefficient, as opposed to Chernobyl's, which had a positive reactivity coefficient. My word, there's an exciting way to run a reactor. So the hotter the fuel it gets, the more it expands and reactivity decreases. Certainly in the fast spectrum, that is fairly obvious. High power density, as Paul mentioned, but low pressure. You don't have to contain it with a dirty, big, thick pressure vessel like you do steam, because, hey, steam is very high pressure. This takes a lot of heat, but is atmospheric pressure. The molten salt is contained with a force-cooled freeze plug. The core is molten, but unlike Fukushima, it was deliberately so. And it has, most designs depict a freeze plug at the bottom, cooled by a deliberate force powered cooling system. If the power should fail, the freeze plug stops being cooled, heat from the core melts it, and it runs off into a choria or a safe geometry drain. The salts are chemically inert, unlike, I don't show the high energy reactions, for example, zirconium or sodium with water. And some of the most hazardous fission products are the gaseous ones. They build up in a fuel pin normally, held in by the plenum spring on a PRR or a dirty big stainless steel jacket on an AGR. And if there's a rupture of the fuel clad, all the accumulated gaseous fission products leave and enter the atmosphere. On a molten salt reactor, you can't stop them leaving actually, but you would bubble them out to help with a helium sparge to take out the xenons and the kryptons. And in the fast configuration, fission products can be allowed to build up in the loop because the capture cross-section of fission products in the fast region is much smaller than the capture cross-section for neutron poisoning fission products in the thermal section. Now there's huge amounts of grounds for development there, and all of these are problems. There are huge problems, but every problem is an opportunity, and the field is wide open for the UK to get in as we have good skills on all of these, and I'll just quickly cover a few. Materials of the core and the piping. These are temperatures where ferritic martensitic steels start to struggle, and especially in the presence of high neutrons, the nickel is another problem. But some Czech and Russian labs believe they have produced materials that can provide containment for the core and the coolant. But there are other ideas out there, ceramic coatings, nitride coatings and all that, so plenty to go at. There are many options for the composition of the salt itself. Nothing new about salts. Aluminium is the electrode one from bauxite. Molten salt is a fairly common process out in industry there. As Paul said, most of the discussions are around the fluorides, but other halides are discussed. Chlorides are discussed. I've even seen people talk about the iodides and the bromides, but I'll leave it to that. Lithium is a problem with tritium. We've got to be careful about that, but that's another topic to be discussed later. And there are many and varied layouts. There's all sorts of different configurations. In some options, the coolant function, the fission process, and the breeding step are all in one fluid. The single fluid choice. In others, the coolant is separated from the fuel. So the two functions are separate loops, two fluid systems. There's all sorts. I've seen a team from Brazil present a case for one that is cooled by molten lead, and the fuel flows through a nest of small tubes, 20,000, very high temperature reactor. They're talking about 1,000 degrees outlet temperature, so a bit of a materials and production challenge there, but also tremendous opportunities. Right, okay. They can operate on the thorium cycle, the plutonium uranium cycle, and many will start with a plutonium load or a uranium-235 load from HEU, and then move on to uranium cycle. They can breed. There are several designs with the breeding ratios of 0.1. As I've said, the xenons and kryptons are sparged out often, but then other reprocessing steps can be done to maintain reactivity by introducing fresh fuel or by removing other fission product if they are serious neutron poisons. There's a last type of reactor, we can talk about more detailed questions. There's a last type of reactor that uses a bit of a hybrid type, uses an accelerator, either a linear or a circular accelerator, to drive a beam of protons at a heavy metal spallation target within the fluid. That generates a shower of neutrons. The benefit of that is it solves a lot of your breeding ratio problems, and of course you can turn off your reactor. It's also critical you can turn off your reactor by turning your accelerator. It does mean you have a dirty big accelerator next door to your reactor building. I'm running out of time. I'll quickly go through the international opportunities. There's widespread activity around the world on both the large scale and the small scale. Paul will just cover the large scale, but on the small scale, there's all sorts. The Atomic Energy Society of Japan have a working group on molten salts. The Paul Scherrer Institute in Switzerland is characterizing molten salt reactor physics. There's work in Canada, there's work in America. There's even the Simon Bolivar University in Venezuela working on an accelerator-driven molten salt system. But there are some very large Asian programs, and Paul will cover those in a minute. In Belgium, for example, they have a thing called MIRA, which is a linear accelerator-driven system, and they're concentrating on partitioning and transmutation of the minor actinides. So there's other ways of deploying it. And one of the other ones is the EVOL scheme at Grenoble. There's a lot of work in France. Some test rigs, but mostly on the codes and physics. So my final summary is the UK doesn't have a civil water reactor of its own and never will have. We don't have a Generation 4 one either, and water one of those. But that's where the opportunities are. And with wit and with coordination of some of the exceptional nuclear pockets that we have of know-how in this country, then we could be medium or even big players in an international programme for reactor design, which is just what the 21st century world both needs and wants. And I'll pass on to Paul now for the next bit.
Thanks, Barry. As thought-provoking as ever. Right, so I'm picking up on the actual global development that's going on at the moment. Barry says there's quite a lot going on in the world at the moment with respect to molten salt development. But the biggest push in the development of molten salts is in China. And some of you might have recently seen the press announcements just after Christmas actually purporting for the acceleration of the Chinese molten salt reactor program. The Chinese energy demand is growing rapidly. They're a rapidly growing country, and despite the world's largest reactor build program that's currently ongoing, the vast majority of Chinese power is still actually provided by fossil fuels, with the invariable impact on their air quality. And I think as we've seen in some of the shots from the Olympic Games a couple of years ago. With China looking to secure its long-term nuclear supply by diversifying into a number of different fuel options, China in January 2011 signed a protocol with the US Department of Energy outlining terms for a joint research program with the Oak Ridge National Laboratory with the Chinese Academy of Sciences. And they launched a strategic research program which was looking at two fundamental elements and challenges in the world of nuclear energy generation. One was the long-term nuclear fuel supply, and the second one was the permanent disposal of spent nuclear fuel. Now the first area, that of long-term nuclear supply, was being addressed through a thorium molten salt reactor project. And basically the signing of the protocol that the Chinese had with the DOE and Oak Ridge National Laboratory basically gave them access to all the historical R&D data from Oak Ridge from the 1950s and 1960s by Alvin Weinberg that Barry's actually mentioned led to the two reactor programs he actually just highlighted. So the Shanghai Institute of Applied Physics, SINAP, is actually, together with the Chinese Academy of Science, have got quite an ambitious program. What the Chinese are looking to do and trying to actually get in place by 2035 is to produce a 1,000 megawatt electric molten salt cooled demonstrator reactor, and also have in place a 100 megawatt electric molten salt fueled demonstrator reactor. So quite ambitious. In addition to that, they're looking to actually pave the road to commercialisation of the processes required to actually develop a proper commercial thorium-fueled reactor system. In addition, also at a smaller level, SINAP is also looking to actually develop a 2 megawatt molten salt research reactor in the next 5 years. And to give you some example of scale, as you see from the numbers up here, it's not a small program. We've got a seed budget of around about $350 million, and they've recruited 140 PhD students I mean, wouldn't that be fantastic if we could do that in the UK? And the aim is to actually increase that to about 750 staff by 2015 and eventually have a research community of about 1,000 researchers working on the programme. But China's actually been looking for international cooperation other than that obtained from the US. And in December 2012, the Australian Nuclear Science and Technology Organisation, ANSTO, signed a Memorandum of Understanding with SINAP to cooperate in the areas of material research and development. And the things they're looking at are things like molten salt corrosion, radiation damage effects, high temperature effects, and weld modelling. They're not wanting to do our Antipodean colleagues down, but with the UK's skills and expertise and R&D capability, surely there must be routes in for the UK to bring our expertise to support the realisation of an international project such as that happening in China. And then there's India. If you think back to an earlier slide on the thorium abundance, you see that India is a country with a lot of thorium. And India have got an expectation that they will actually supply about a quarter of India's energy from nuclear sources, up from the current 3%, and that thorium as a fuel will play a major part. And last year, in March last year, India made the press announcement that they'd actually launched a new nuclear reactor program with thorium at its centre. But that program is actually primarily around the use of solid thorium plutonium fuel as an energy source for fast breeder reactors and then ultimately breeders through their advanced heavy water reactor program. But also there's a lot of research going on molten salt reactors as well. And this research is being led by the Baba Atomic Research Centre in Mumbai, BARC, and they're currently undertaking analytical research, so it's paper-based research looking at best options for molten salt reactors in terms of things like fuel utilisation, breeding ratios, moderator lifetimes, deciding what type of reactor is best, whether you're talking about thermal, epithermal or fast reactor. And this slide just actually shows a couple of molten salt reactor options that BARC have considered potentially worth pursuing. And I'm not going to go into details of those. The slides are going to be made available and the links are on the bottom, so hopefully you'll be able to find those on the web. So what can the UK's contribution be to molten salt reactor programme going forward? We all know that these international programmes all have considerable challenges. Barry's actually mentioned a number of challenges technically to support the delivery of molten salts on a commercial basis. But we have to look at these, as Barry said, as opportunities. But it's worth noting at the moment the UK not only has any input into the Gen 4 reactor programme, it's got no major programmes associated with molten salt reactors. That's not to say that we haven't actually got the capability or skills to actually contribute to the molten salt reactor programme. The UK has a rich heritage in R&D, and many of you will recognise the old UKEA sites, currently now owned by NDA, where that R&D was actually undertaken. And some of that R&D actually included molten salt reactor R&D. For instance, back in the 60s through to the mid-70s, down at Winfrith, there was research done into the concept of looking at a 2.5 gigawatt electric molten salt fast reactor. And they initially looked at the thorium uranium-233 fuel cycle, but ended up looking at the uranium-238 plutonium fuel cycle for a molten salt fast reactor. And then at Harwell, there's a joint BNFL and AAT programme looking at molten salt actinide electrorefining experiment using uranium chloride. So we've got elements in our heritage which actually have undertaken molten salt type of work or direct work in the past. In addition to this heritage, that's not stopped there. Even today we're actually building state-of-the-art facilities like those run by National Nuclear Labs and also Dalton Institute. And because of our rich national heritage in the nuclear industry, and many of us and many of you in the room are actually part of that legacy, we have a considerable experience of understanding the whole nuclear fuel cycle. That's right from fuel fabrication through to fuel processing. And the knowledge and experience of actually developing and running sites like Sellafield over the last 4 or 5 decades has really given the UK an enviable position with respect to understanding of things like radiochemistry and associated subjects. And we have centres of academic excellence that are growing resources available around the UK to potentially support MSR development, such as Dalton Institute here in Manchester, Oxford, Cambridge, Imperial and others. And then there are other assets around the UK and capability and projects actually ongoing which have got links or potential links into molten salt development programs. And there's just a few here that I've put up to actually demonstrate that. The Nuclear National Labs have their molten salt test rig up at Cumbria as a legacy from investigating the use of molten salts in research to support the use of nuclear material reprocessing. And there's several of you here from Nuclear Labs today, and you have your own expertise in radiochemistry and molten salts and pyroprocessing. Then you've got the REFINE project, and that's a UK coordinated research programme led by the University of Edinburgh, Professor Andy Mount, which many of you may know, with other universities including Cambridge, Nottingham and Manchester, as well as UCL in London, again in partnership with NNL. And that project is aimed at actually delivering material science required for sustainable spent fuel reduction in a closed-loop nuclear energy cycle. And a key element of that research programme is the establishment of molten salt analysis techniques and the establishment of inline sensing technology required for pyroreduction systems. I'm sure the R&D that's been done as part of this programme could be applied to a molten salts research, molten salts reactor programme. As Barry mentioned, EVOLVE in France, there's an Oxford-based molten salt expert, Professor Paul Madden, and he's collaborating by providing advice in the area of the properties of molten salts that are undergoing fission. And he has a computer code, a world-leading computer code, that allows him to actually compute the properties of molten salts mixtures of various types. We have world-leading material scientists such as James Professor Marrow down at Oxford, who's applying his research on material degradation to a number of Gen 4 reactor programs. And then more recently, Greg Butler's here in the audience today, and you might have seen the article in Nuclear Future. Under DEC sponsorship, a generic feasibility assessment methodology has been worked up, and recently a workshop completing the assessment of molten salt reactors was undertaken using the GFA technique. And finally, there's Bob Cherinsky's work in the International Institute of Accelerator Applications at University of Huddersfield, which looks at the accelerated driven subcritical reactors that Barry was just talking about in the last part of the lecture. So the UK hasn't got a blank sheet of paper to actually start from. It has a base from which to build if we want to actually get into molten salt reactor programs. The Chinese are obviously going ahead with their programs, and as Barry discussed, there are smaller projects. So in that vein, is entry into the molten salt market and the molten salt development wholly dependent on the UK getting into an international collaborative environment? And is that inevitable in today's economic environment that we find ourselves in? As I said, those programs actually have significant challenges, whether it be fault studies, reactor physics, salt dynamics, reprocessing, structural materials. We've already mentioned quite a few of those today. And as I say, for repeating myself, we should look at those as opportunities for the UK. In developing expertise and bringing the UK's legacy of science and innovation to bear to address these issues could be that significant entry route into Gen 4 collaborative international programme. So that addresses the first point. Secondly, could we do something in the UK by ourselves? Could we go alone? There's a significant amount of expertise that we've seen actually that resides around the UK, but it's different today than it was back in the 60s and 70s and 80s. It's more disparate, it's spread around the country. It hasn't got the single focus that was around when we had BNFL and UKA driving those R&D programs forward. So collaboration and coordination of those various skill centres will be really key if we're looking to actually build upon that to drive something forward which may be able to actually drive forward a UK MSR design programme. And just to highlight, we do have individuals actually within the UK. We've got Ian Scott in the audience today, who's actually driving forward their own innovations in the areas of molten salt reactors with Ian's simplified molten salt reactor concept. which uses static molten salt relying on conduction and convection to remove the heat from the core. And this is a revisit of an MSR design which was cast aside in the 1960s. Now, I'm sure Ian will gladly be able to tell you more over a glass of wine or a glass of beer of the food and the canopies later on. And finally, what about wider industry? What can wider industry do to actually support molten salt reactor programs, be it internationally or if we decide to go it alone in the UK? And how can engineering companies such as Atkins, with our major infrastructure experience, actually support such programs? Well, links from R&D and research into commercialisation will always need the support of industry, providing engineering design expertise that builds upon the science and R&D that's been developed to actually get the project through prototyping finally into a full commercial deployment state. And if you look beyond where we're looking at the timescales for the deployment of Gen 4 reactors, of which molten salts is one, Atkins has already played a major role in supporting the delivery of fusion technology, with its role as part of the Octa Engineer joint venture for ITER down in the south of France. So research, development, prototyping, as I said, will always require support from industry to realise those technical visions. And those collaborations as well, going back to UK's history, we've had a real good track record in actually international collaboration, which has pushed some fairly innovative and technical leading projects forward, and there's just a few on the board here. And all those international collaborations have involved global engineering companies in the realisation of these opportunities. And when you look at a company like Atkins with our global reach, with our presence in China, India, and you compare that to the landscape for molten salt reactor development, then we're fairly well placed to actually play a facilitating and supporting role in any UK project overseas, if that's what UK in fact chooses to do. So just wrapping up then and summarising where we got to and summarising what we've spoken about today. Just picking up on Barry's point, it's been 13 years since 9 countries formed the Gen 4 International Forum to review and to sponsor development of new reactors, which would actually be a significant step change from the reactor designs of today. But as Barry said, we have no current UK involvement. Though, as you stated, one of the most interesting of these, and probably most technically challenging, which have got to be seen as the opportunities, but potentially the most beneficial, is the molten salt reactor. We've seen that the molten salt reactor is not a new concept, having been demonstrated by Oak Ridge National Laboratory in the US in the 1950s. So could this old concept be one of the technology solutions to meet the future needs of the UK and globally? We know that some countries think so. As I said, China are really pushing on with their plans to build a fully functioning MSR within the next 10 to 15 years. We know that for the once-through process that Gen 3, Gen 3 Plus technology is not sustainable in the long term. The uranium resources won't allow that. So it's important that Gen 4 has to happen. And it's important that the UK, to note that currently the UK has no intellectual property in Gen 3 or Gen 3 Plus technology, and never will. Perhaps we can solve that within Gen 4 programme. So the UK has to play a role in Gen 4, whether through international collaboration or whether we go it alone. And as we've seen today, that role could be in molten salt reactor development. If the UK is to get involved in molten salt reactor development, international collaboration, what will the UK's unique selling points be in terms of actually what we can offer international programs? And whether that's in salt dynamics, salt reprocessing materials, just examples of the sort of things to do. I believe what we need to do is actually to identify those niche skills and technologies that are still representing those challenges, and actually put those up against the expertise and know-how that resides within the UK to ensure that other international molten salt reactor programs realise that they can't do without the UK, that the UK can deliver answers to those challenges, and that has to be our first priority. And if successful projects, most successful projects are generally associated with the vertical integration of capability as well. So somehow we've got to actually integrate our academic, our R&D institutions, engineering, design and manufacturing capability to actually all play their part in going forward. and whether we look at the UK supplying niche technology into an international market or delivering a UK wholly designed molten salt reactor, then delivery using this integrated model could be the answer. But looking serious at molten salt reactors could present the start of a multi-million-pound programme that not only helps provide sustainable energy and security supply, but meets CO2 emission targets for the UK, but significantly provides an opportunity to the UK PLC to export technology rather than being the recipient of international technology as we currently are with Gen 3, Gen 3 Plus programmes. I'd just like to end on the positive note that, yes, as I highlighted in my first part of the talk, we currently have a real positive focus from government through the nuclear industry strategy, the establishment of NIRAB and other initiatives. And we could be on the dawn of I hate to use the word again, it's been used recently, but the dawn of a potential nuclear research development renaissance. It's not a loved word, but we could be on the verge of a new nuclear research and development renaissance. We just need a technology or technologies to grab to move forward. And we, the UK, should not miss this opportunity to actually really add something to the future development of nuclear technology in the Gen 4 arena. And coming back full circle to the actual question that I posed at the start, could that opportunity, could the realisation of that opportunity involve molten salt reactors? And on that, hopefully positive note, I'd like to just thank you for listening. Thanks very much.
David Claxton, National Nuclear Laboratory. First, can I thank you for the free advertising? That was always very helpful. In terms of the reactor design, initially when you were saying it, we need a British design so that we've got a Gen 4 molten salt reactor that's all ours. After a while, it seemed to be that it's more collaboration. Now, these things aren't cheap in terms of, you know, it's like getting a demonstration reactor out there. Do you see it as a collaboration of which the UK has particular skills and things, skill set that it brings to the party? Or is it that we go it alone and we build our own reactor and we take the hit in terms of the cost because of what we're looking for in terms of the end result?
I apologise if the emphasis came across slightly wrong. I was trying to pitch it as an either-or rather than just going down one route. So I was saying the solutions could be international collaboration, or we could go down a UK, solely UK MSR reactor design. Personally, I think it's international collaboration. That's actually where it roots. And that sort of marries up with actually what's been said within the nuclear industry strategy as well. I think to actually go it alone, to actually develop a molten salt reactor design of the UK and not actually generate and use the benefit of what's actually going on in the rest of the world, I think will be slightly naive and probably not the best economic approach to develop new molten salt reactors. So personally, I think the most likely route is international collaboration, because that's where we can actually identify where we've got the greatest input into these international programs, that we can add a real value. That doesn't mean, though, that you know, what we should be looking for is some form of almost intellectual property within that actual reactor program, so that we can actually have something as UK PLC to actually be part of a worldwide reactor program, and not ending up in the situation that we did with the magnets and the advanced gas reactors, where we couldn't really participate in what the rest of the world were doing because they were basically going down the light water reactor route. So I think international collaboration will be the way that the UK would like to go.
It was on the table, as every question is on the table. That's the whole point of the debate here. They're on the table. My own view is that it's not so much the Chinese money and the people that are thrown at it, it's the timescale. If you look at the 2030, there are several changes of government between now and then, and that's several changes of opinion. So I'm not sure that a British design reactor, even if the money was available at one point in time, would continue to be available through to the conclusion. I think patience would have run out before you got to there. And my stance at the minute is we can make a start now. We don't have to wait for a brilliant UK design and the world beating a path to our door. We're no longer the world's university. And we've got to stop acting like the world is going to come to our nuclear door. We have to go to their nuclear door because it's China and India that are spending the big money. And we have to just eat a bit of humble pie, forget UKEA being at a level gone, and think, how can we get a piece of that action? And I think everything that's been said from people all around this room is the amount of talent and abilities, know-how and experience we've got lurking in this country, all spread around now. Because what happened when BNFL and UKA went, to my view, is they cut the flagpole down. All the people are still there, all the pockets of know-how and knowledge are there, but the rallying point has gone, the central rallying point. And that's all we need, I think, now, is a bit of leadership to say, for a small amount of funds, we can pool together all this expertise. The sort of TSBs, chicken money compared to what the China, it's just they spend more on paper clips. I mean, it's just a tiny amount of money we could align, coordinate, focus, match to the customer's needs, using industry partners who have got penetration already in China and India to start getting on this bandwagon. And once we're on it, then all sorts of other things in materials, in salt dynamics, in neutronics, all the other stuff, pyro reprocessing, all those opportunities will build and build and build. So, yeah, I'm not for a UK reactor. I'm for getting started now on piggybacking on where the money's being spent. Sorry, there's a question behind you.
Yeah, Charles Russell Johnson, Sellafield Limited. I just wanted to ask, you say we've got 16 to 17 designs for the actual reactor section, concepts for the molten salt. Now I'll assume there are several different design concepts for the powertrain on one side of that. But have we got any really viable concepts for the real-time reprocessing, fission product concentration, encapsulation, etc. systems that are going on the other side of it? Has anyone paid any real attention to that? And
well, the concepts of how the configuration of how they work, there's any number of ideas in the thermal, the epithermal or the fast neutron spectrum, obviously moderated and non-moderated. As I said, there are some that are burned out and ditch. Some show a Brayton cycle using high temperatures, and some the straightforward Rankine steam cycle. On the pyro reprocessing side, there's lots of ideas about how to do it. I'm not so sure I know of anybody, somebody else might know of a team that has built a molten salt reprocessing in-cycle loop that's successful. I don't recall that, perhaps somebody else knows. But there's how much reprocessing you need to do to your loop depends on whether it's a blanket loop that you're trying to extract fissile material to feed back into the fuel loop, or whether it's also the fuel loop, in which case you're trying to probably extract neutron poisons and leave the minor actinides and the transuranics in there. So that's a field of opportunity. But there's people around here who have been reprocessors, man and boy, to be fair. And we have expertise in this country on reprocessing, up to our armpits. NNL have got a huge amount of know-how. They've even got a rig that they could do salt work at Workington, all just convertible to this purpose at short notice. So no, I don't think, I mean that's one of the great advantages of the molten salt reactor. It's not like LWRs, which are effectively commoditised, to be honest. There's no sort of input the British can make on LWRs apart from like whatever check EDF asks us to pay. There's no input we can put on this field with our talent, as Paul says, and he's given you a list. These are the places we can make money as a PLC. And instead of acting like the world's university, where we're going to sit here in solemn splendour, people coming to us, we need to go to them with our opportunities and our talents and try and make money out of it.
Yeah, Tom Easter, mechanical engineer at Atkins. Firstly, thanks very much. I'm sold. So my question is, how do you perceive the role of the UK government if, except for the funding side, we have to sell ourselves on the international market? Do you feel like we can do that as an industry alone, or do you feel like we need somebody from government or an organisation within government to actually help us sell ourselves on a collaborative basis?
I think, I mean, something that's actually been put in place at the moment as I said earlier on, and I know Gordon Bryant's here from NIRO. The Nuclear Innovations Research Advisory Board is really in its early phase and early days at the moment. And really, in terms of actually focusing what the UK does across nuclear industry, nuclear research and development, across near-term, medium-term and into the long-term, is really the role of NIRAB. And as I say, it's early days, but you'd hope that actually the work that's actually been done in the auspices of NIRAB will start to actually focus what the UK needs to do, start to actually provide some of maybe the leadership that Barry's actually talking about, and providing the focus and collaboration to the various entities that can support the R&D programs which are put through NIRAB to provide advice through to government. So I think, you know, we're at the start of a beginning of something new. That's why I said we're at the beginning of a renaissance. I mean, when was NIRAB, the first meeting, Gordon, was just before Christmas? End of January. So it really is early days. I mean, the government are putting facilitative measures in place to actually help trying to organise, and there are other things. I think there's the Nuclear Facilities Users Collaborational Centre. I think that NNL are actually coordinating various nuclear research elements around the UK to act as a more global UK entity. So there's things that are actually happening. So I think, you know, if you ask that question 2 or 3 years' time, Tom, I think we'll know where we are. I think it's early days, but I think the government's definitely putting some right things.
There's a lot of private sector involvement now with terrestrial energy. There's TerraPower in America. There's supported by Bill Gates. Other companies here. Ian Scott's here. Because there's lots of private sector involvement now, ideas from them. Then the catalyst model, where the government just supplies gets together with industry and supplies the big expensive bits that they all need. So the big infrastructure, so they can make use of shared assets to evolve their own ideas, and then the best ideas sort of win out. I think the catalyst model might well work, as long as there's enough private sector startups willing to have a go at it.
Yeah, my own view on the government is I don't think that we should frighten politicians by looking for mega money. I don't think we spend mega money in molten salts yet. I don't think we're at that stage at all. I think we need micro money at the minute. I think we need micro money, but a different way of thinking about how the British comport its nuclear industry. Not of how can we establish a super duper research programme to support something clever. We're not the world's university any longer. How can we use a small amount of money on TNS, more or less, and perhaps a few key people brought together to suck out of where the know-how is lying around and coordinate it in a you scratch my back, I'll scratch yours, into some of the markets where people have money. Now, the UK PLC can't afford big nuclear programmes. People are struggling across this country. We can't afford it. And to go to the government and say, give us £700 million for some dream, we'll just brass them off. I mean, it's a bad word, but brass them off. I think what we'd like to have is enough funds, just pump priming, lubrication funds, small amounts, just to get the UK's pockets of expertise identified, coordinated, work out a contractual model so all participants, even NNL, can make some funds, Atkins can make some funds, any other participant can make some funds out of some proposal, capturing this know-how, selling it like ANSTO and ONL have done in the markets where they have money and they're looking to spend it on MSR and its progress. And see what bedrock of expertise we can build up, and that might take us on to another place with another set of opportunities. But we should look from opportunities all the time and not think of nuclear as a great church we worship in. It's a money-making racket. And who's got the money and how do we get them to spend it on us? That's what we should be thinking of.
You did mention, that there was a need to sell the UK. It's already happening through UKTI, UK Trade and Investment. Lots of people have heard of UKTI as the organization which promotes export, but there is also the other side which focuses on inward investment. And we've been mapping out the capabilities of the UK supply chain, and we are approached by foreign-owned companies interested in investing in the UK. And you know, that's something that we need to bear in mind, that it's not just R&D driven. And when you look at existing companies investing in R&D, well, in terms of account management, all the departments of the government are collaborating across Whitehall. When we look at companies like Atkins, Horizon, you can be sure that there are virtual teams sharing that market intelligence. And that's a shame that not lots of companies are aware that this service is free, and we should build on it.
Yeah, very good point. Thank you very much. So on that note, can I draw tonight to a close? I hope you've enjoyed this evening. It's been quite a lively debate, quite a lot of different views actually expressed. Slightly longer than planned. I know you're all chomping at the bit to get down to those canopies and wine and beer. So drive safely going home when you eventually get there. But thank you very much for attending tonight. I've really enjoyed it. Thank you very much for your questions. So it's been great. Thank you.